All right, we are now recording. Let me go from current slide. And boy, I don't know of many announcements except this, and I wish more people were here. Have all of you done the student course evaluations?
Nope.
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 Nope. Come on, folks, please get those done. Technically, I mean, not technically, I've actually seen it from the dean's office saying, don't give the final exam until they do the student course evaluation. I don't believe
do that.
No, I don't believe in doing that. So I just ask you, please do the student course evaluation. What's that?
They're trying to find some way to encourage us to do those surveys, but what they don't realize is we don't want the final either.
Yeah. Well,
so we'll hold that off until the last minute. You'll have to send in grades. You're gonna have to put in something besides a zero for the final. We get to the end and we're just like,
the other side of that coin, when you try to force someone to do something, I'm not sure you get a fair reading. I think you might make people mad and they just put down really things that they're just responding to being mad, not to how the class went. So I think it's counterproductive. But that's just me, I guess. Okay. But anyway, please do the student course evaluation. We do pay attention to them. We try to use that to improve our teaching. I use it when I'm evaluating my instructors. You know, that's one of the things I have to look at. So please do them. I know you don't like doing them, but please do them. They don't take, but has anyone done them? I guess not. Someone in another class once said 5 minutes. That's all it is, 5 minutes of your time. Please do the student course evaluation. Okay. And we're going to continue in Chapter 4 as far and as fast as we can today, even though we've got a late start and slow start right now. But we're going to continue with Chapter 4, and then at the end I will give you your final exam, which is Test 3, by the way, just on Chapter 4. Now, the question is, have all of you who are present turned in the first 2 tests? Yes, 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 yes? Okay. Well, then I can return those except those that returned them this morning. I don't have those graded yet, but the others. Now, I cannot return your research paper. And let me say this, too. I don't have the grades in Blackboard yet. Last week's planning hearing wiped me out for actually more than a week of getting grades done. So this weekend, every spare moment I had, I was grading, and I reduced my stack from about 3 or 4 times this thick to that thick, but I still don't have them all graded, so I don't have everything for you. All right, good deal. Thank you. Okay. Now, while you were here, I wish I had given you this. There's your test 1. Now, you don't know if others haven't turned these in yet. So I would say to you, please don't spread this around, because otherwise someone will see the correct answers, which I mark on your paper, and then that will cheapen your grade if someone hasn't turned it in yet. So be kind of protective of these.
I turned it in, you can show me. I gave it to him like 5 minutes ago.
Okay, there's test 1. And all of you said you had to in test 2 as well, right? Keita's not here. Shakina's not here. Lauren, yes. Jasmine's not here. Tina's not here. David's not here. So I think the others of you turned it in today, right? Please tell me yes. Yeah, okay. I remember all of you turning something in, but I didn't look to see what it was. Okay, so I've returned everything I can. When you come to turn in your final, I'll give you your other test back. And by that time, knock on wood, everything should be on Blackboard. Okay, I did mark or in here. All right. We left last time with this, and I think we had already discussed it, so I'm not going to do it again. I'll just zoom in and let you see it once more. This is L'Hopital's rule, and Davis is here. And if you'll get with me right at the end of the class, I'll return your other pages. I've already returned them to the others, so to keep from slowing down the class anymore. We did this last time. L'Hopital's rule works anytime you have a anytime that you have a 0 over 0 as x is approaching something, or an infinity over infinity as x is approaching something. Either one of those, L'Hopital's rule will work. Okay? Even as x is going to infinity, if the ratio here is 0 over 0, L'Hopital's rule works. Take the derivative. If it's infinity over infinity, take a derivative. Plus or minus, by the way. Keep taking derivatives until you get some form that either will not work or gives you an answer. And here's an example, example 10. Okay? Which of the following two functions, f of x is equal to x squared, let me get my pen set up, and g of x is equal to x log x, okay? Which of those grows faster as x approaches infinity? Okay? Now, how will we answer that question? Which of these grows faster?
Like 5, see which number is bigger.
Okay? That would be a good thing some of the times, but some functions literally do this. For instance, this one doesn't. They show you the graph here, and with the graph in sight, then one's answer probably is fine. If you haven't got the graph, some functions do this. One function starts fast, but then slows. The other function starts slowly, but then takes off and goes. If your 5 is before they flipped, then you get the wrong answer. Yeah, 5 would be better on this one, but when you get to 55, the other one's way ahead. So we don't always know if that is. When you got the graph like this, yeah. Well, when you got the graph, you look at it and say, x squared wins, okay? But you don't always have the graph. So doing it, what would be another technique besides ones, okay? Okay, ultimately we will do that, but what we're going to do is look at the ratio of those. If the ratio comes out greater than 1, f of x wins. If it comes out less than 1, g of x wins, right? So let's consider the limit. Now remember, this is a limit as x is going to infinity. That was what the question is. So what we're looking for is a limit as x is going to infinity of x squared over x log x. Okay? Tina's here. Okay. And if you get with me right at the end of class, I'll return your other tests to you. I've already returned them this morning. I don't want to hold up class any longer. Okay, so there's our question. Who's going to win? Is that limit going to be greater than 1 or less than 1? If it's greater than 1, x squared, what's the question? Grows faster as x approaches infinity. If that limit is less than 1, then that means x log x grows faster. What would be the next thing you would do? Any ideas? Make a guess. If you had that ratio to look at and you're trying to determine what the ratio is, what would be one thing you could do to simplify it? If this were Math 100, and we had done logs. We usually haven't done them, but Math 112, we do logs in that. I ask you to simplify that ratio. What would you do? All right, x divided by x is 1, so divide out an x. That'll make an x in the numerator and wipe out the x in the denominator. So that's our new limit is, as x approaches infinity, of x over log x. Now, frankly, I know what the graphs of those look like, and I know, like Juan was saying, x is going to win. Okay, in the long run, it's going to get. But without doing that, then we would tend to, if you could plug in infinity, what happens to x as x approaches infinity? It approaches infinity. What happens to log x as x approaches infinity? It approaches infinity. But I know it approaches it more slowly. But how can we show that? Yeah. This is for Juan's idea. Take a derivative. Okay, L'Hopital's rule says if you have a rule for limits at infinity, if you got an infinity over infinity, then take a derivative. Okay, so let's do that. That would be the same. L'Hopital's rule tells us the same as limit as x approaches infinity of one over one over x. Okay, and what's that one? That's the same as 1 divided by 1 over x, right? That's a division line, right? And that's the same as 1, when you're dividing fractional forms, what do? Flip it, okay? X over 1, which is x. And as x goes to infinity, where's x going? To infinity. So guess who wins big time? The numerator. Infinity is a great deal larger than 1, so therefore the numerator, x squared, goes to infinity at a more rapid rate than x log x, which one could have gotten using as 5, but we didn't know for sure if that would work. But sure enough, that does work. Okay, so we know that here's our conclusion here, in case you ever do it. X log x is a great deal less than x squared, okay, as x goes to infinity. And then you look at the graph and say, oh yeah, we knew that. Okay, good deal. Now, let's go on to example 11, which I think is one, well, maybe it does have. No, it doesn't have a graph. So let's just clear this and go. Oh, I'm sorry, I should have asked. Were there any questions on that before we moved on? Okay, let's do 11. Jonathan is interested in comparing two computer algorithms whose average run times are approximately log n squared and the square root of n. Okay? Which algorithm takes less time for large values of n? So now we're wanting to know not who's the fastest, but who's takes less time. And these are the run times. So what are we going to try? How do you do that test? We say, which of these two these are the run times. Which algorithm takes less time? at large N. And we don't know if 5 is big enough, is large enough, okay? So what are we going to do? Not too dissimilar from what we did before. Second, a ratio, okay? What ratio you want to do? Okay. Log n squared to square root of n. Now, they went and changed to x's. I'm not really sure why. Replaced n by the continuous variable x, which is fine to do. But let's just pretend n, we know it really isn't, but let's pretend it's a continuous variable, okay? It may not be. They don't even tell you what n is. I think that's number of operations. But so it isn't a continuous variable. You can't have 3.4 operations, so you can still treat it like it's a continuous variable. Or you can change it to x's. Now, the book happens to flip them. It doesn't matter. What we're interested in is who wins. If the one on top is larger, then that ratio is going to be greater than 1. Then the one on bottom is going to be less, right? Okay? And vice versa. So it still will work. So what do we do next? 1. One of those questions. Oh, very good. Good idea. I'm glad you thought of that. Okay. Now, how do we take the derivative of log n squared? And now, I didn't ask when the last few of you came in. Have all of you turned in both of the first 2 tests? You have. Have you, Ivory? Okay. Okay, right. Do you have them ready today, or you need more time? Okay. I can take them anytime you got them. Okay. Yeah. Okay. There wasn't any issue with it. I just wanted to know so I could get them. And I was going to I've told the other 2 when they came in, at the end of the class, I'll return everything to you, but if you turned in the first test, though, right? So I'll return it to you at the end of the class. I already returned it to the others, but that's why I was asking, because I will return it. So the question is, what's the derivative of log n squared?
Would be 2 log n.
2 log n. Maybe there is an advantage for doing x. You don't have ln n, you know, but there's more, isn't there? Chain rule. Anyone? No, you already got the log n. 2 times log n times derivative of log n, which is? Say again? 1 over x, or 1 over n. Exactly. So that'll be over n. I probably should have gone to x's, but it's okay. And how about the denominator? Well, I don't like taking derivatives of radicals, so what could we have done? N to the 1/2. I like taking derivatives of powers. Okay, what would that be? 1/2 n to the negative 1/2. Okay. Now, let's do what we can do with this one. First, I'm going to go write the limit anymore. I'll come back and write it later. So this is 2 log n over n. Let's just go on and do a divided by, and let's go on and do this one. What is this? This becomes an n, 1 over n to the 1/2, right? So that's just 1 over 2 n to the 1/2. Does everybody buy that? Okay, that's exactly what that is. I just moved it downstairs and wrote it as a fraction there. Now that's the same as 2 log n over n times 2 n to the 1/2 over 1, right? Invert and multiply, right? Now, what can you do where? Anything? To simplify? Okay, kinda, not quite. Okay? Square root of n will go into n the square root times, right? Because this is exponent 1, and you're doing exponent 1/2 into that, so it's like 1 minus 1/2 will give you 1/2. Does everybody see that? Okay? Was that too much of a sleight of hand? Okay? Now what we've got to do is take the limit as n approaches infinity, or x approaches infinity, of 4 log n over n to the 1/2. What happens is that is going to infinity. What form do you have? Infinity over infinity. So what do we do? L'Hopital's rule again. Okay, and how do we do that? Take a derivative. Very good. And what will that be? Say again? No, it is log n. You're taking a derivative of log n. What would that be? Okay, 4 is certainly there. What's the derivative of log n? 4 over n. Very good. Okay, with prompting. Okay. Now, how do we take the derivative of the denominator? 1/2 n to the negative 1/2. Seems like we've been here before, doesn't it? Okay? All right. So let's write that in fractional form. That'd be 4 over n divided by, let's start with a divided by, and that one again becomes 1 over 2 n to the 1/2 power, because it was, okay, I'm taking out of the denominator, making a division, but then I'm moving back in the denominator because of that negative radical, the negative exponent, okay? Now what do we have? That's the same as 4 over n times help me? 2 n to the 1/2 over 1. Okay? And again, n to the 1/2 will go into n to the 1/2 times. So now we have, and this is a limit as n approaches infinity, of 8 over n to the 1/2 power. Okay? By that? Now, what happens to that as you let n approach infinity? 8 over infinity, which is that getting smaller, approaching 0, right? Doesn't ever get there, but it's approaching 0. The limit of that would be 0. And is 0 less than 1? Yes, it is. That means the denominator is getting bigger faster than the numerator. I mean, just look at this. This is 8. This is the square root of n, okay? And if you had chosen 5, okay, I'm sure you would have chosen 5, square root of 5 is less than 8. So that wouldn't have told you the right answer on this one. But if you chose the square root of 50, the square root of 500, then that would be, because square root of 50 is still less than 8. But the square root of 500 is way bigger than 8. So in the long run, the denominator is bigger. Okay? What we're looking for, which takes less at large n, less time at large n, is that numerator. And that would be the log n squared. Okay? Somewhat surprising. Okay? No, it isn't. Okay? And let's see what the book came up with. Shows that log n squared is a good deal less. That's exactly how this is. Log n squared is a good deal less than n to the 1/2, wasn't it? Yeah, so square root of n. Okay, and that's what we saw, even though we looked at it in the reverse order. Doesn't matter. All you're looking is at the ratio, who wins? Who winds up bigger, smaller? We were looking for smaller this time, so we wanted the one that was smaller. That was the one on top, and I think it was Davis gave me that told me to put that one on top. It works. They used it on the bottom, and they wound up with the going to infinity. So the top one took longer, the bottom was simpler. Okay, took less time. Good deal. Any questions on that? All right. Now, I don't know if you remember back in section 1.6, I don't think we did 1.6, but when you did it in pre-calculus or whenever you may have done something like that, it was asserted that exponential functions increase more rapidly than power functions, okay? And we now prove this by using, guess what? L'Hopital's rule, okay? So this is we want to show that x to the n is what the book claimed is a great deal less than, I put the wrong thing, a great deal less than why did my n, well, I guess it was just an ugly n to begin with, wasn't it? X to the n is a great deal less than e to the x. So how can we show that? Tell me. How do we do it? I heard L'Hopital's rule. What does L'Hopital's rule always involve? When do we use L'Hopital's rule? Say again? Well, you do it, take a derivative, that's what you do with it, but when do we use it? Say again? When what is? Okay, the fraction you have, and what you're trying to do is look at the limit as x goes to infinity. So that's what you do. It always deals with the limit. So it's a limit, this time as x goes to infinity, of what? Which one you want to look at? And you set a ratio, what's going to be your ratio? What's going to be your ratio? X to the n over e to the x. Okay, looks pretty good. And what we're wanting to see is if that ratio turns out being greater than 1, the numerator wins, or less than 1, the denominator wins, meaning gets bigger. And that's what we're looking for. Which one increases more rapidly? So, according to what Juan just told us, what do we do? Take a derivative. What does your numerator give us? N times x to the n minus 1. Okay? Over Say again? E to the x. Very good. Okay? Now, and actually, they're going to do this in a different way, okay? Because we could sit here all day and keep doing that, and we keep getting infinity over infinity, because we don't know what n is. So what they suggest that you do is start with n equal 1, okay? So let's go back and do that. N equal 1. Okay? Let's start with that one. We'll start with this with n equal 1. And what would that limit be? Take the derivative of x. One. Okay, boy. I feel like a dentist there. Who wins here? Which gets bigger faster? As x goes to infinity. 1 or e to the x? E to the x by big time. Okay, so certainly when n is equal to 1, you know, e to the x wins. Let's try limit. Okay, now this technique that we're using is called, and they may not tell you what it's called here. Yeah, they do. It's the principle of induction, okay? And it really is going to take a little more time than we have to show you this from scratch. But let's just do it for another one or two. X approaches infinity to when n is equal to 2. Okay? That'd be x squared over e to the x. And what would that be? Doing L'Hopital's rule. Two x over e to the x. What does that tell us? Say again? Over infinity, we can't tell there, so what do we do again? Take it again. Do L'Hopital's rule again, and what does that give you? 2 over. Okay. Now, if you keep doing this for more and more n's, notice what your derivative winds up being. A number, but always e to the x wins. The higher the n, the more times you got to do it. But at some point, because n is a finite number, you're going to get to some number, and e to the x is always going to win, right? So this, if we had done it properly, that would have been how you did induction. You can read in the book and see. You let n equal k, and then do a few, and then do k plus 1, and show that it's going to be always greater. So, yeah. But this gives you the idea. If you went to n equal 3, you just have to do L'Hopital's rule 3 times, okay? And you'll wind up with 6 over e to the x. You do it 4, it would be 4. It's n factorial over e to the x, okay? But with n being a finite number, that's just a number, e to the x keeps going infinitely large. So therefore, here's the conclusion. We'll just show you here. And because we're so short of time, I don't want to take too much, and especially to show you how to do proofs by induction. But growth of e to the x to the n is a great deal less than e to the x for every exponent n. In other words, and they flipped it over, okay, the limit is e to the x as over x to the n is always going to infinity for any value of n you put in there. The way we did it, we had x to the n on top, e to the x on the bottom, it went to 0. So therefore, the e to the x was larger than x to the n. A great deal larger. You get far enough out there. Okay. So there's something to remember. Now, they do a little proof of L'Hopital's rule here, but they don't do it on the slide set, and I'm perfectly happy they don't. So let's do, any of you want to do the preliminary questions? I'll be glad to if you want to. Yay or nay? No. Okay. Homework exercises then are any of the odds 1 through 9, any of the odds 11 through 15, any of the odds 17 to 53, a whole bunch of them there. Okay. And then any of the odds 55 through, wow, I'd say 71, and then either 73 or 75. I'll let you decide. Okay. Now, looking at the further insights and challenges, there is something there about resonance. We've already mentioned L'Hopital and how he developed his rule. Did he develop his rule? All those kind of questions. Those could be paper topics. And I just wanted to remind you, now some people may have turned in today, but so far as of the weekend, I only had 4 out of 11 people turning in papers. Okay? What's that?
I'm emailing it to you.
Okay. I will take it, but you know I have to grade what I get. So if it comes out screwy through the email, that's what I have to grade. So that's fine. I'll do it. Just letting you know that's the situation. Most of the time they come out fine. But I have had some come off. The format looks terrible. Now my guess is the format was terrible when they put it in. They just didn't realize it because they hadn't printed it out to see it. But it could have been that the email itself screwed it up. That I don't see how, but it could have. But I have to grade what I receive. Okay. So anyway, please get your papers. So get them today. You just get your score. No bonus points today. Okay. If I get them anytime after today, you start losing points. Negative. Disbonus, unbonus points. Okay. You start losing points. Okay. Now. So let's move on to, if you don't want to do any of those, we will move on to 4.6. Goodness gracious, this is slow. Here we go again, starting PowerPoint always. But this time it's actually doing something, so it did get there. So let's do the slideshow. Current slide. Okay. Now this is a bit of review here. I sure hope it's review for you. All right. This is a table that summarizes what we've already talked about. Let's first look at, okay, you've got some function f, whatever that function f is. Take a derivative. And if you got that first derivative of f, if that is positive, you know you got an increasing function. If that's negative, you know you got a decreasing function. If it's 0, that means you have a horizontal asymptote, but you can't tell you much else besides that. Either increasing or decreasing at that point. So you have to look. You also do a second derivative of the function. Okay? If the second derivative is positive, that means you're concave up. The second derivative is negative, that means you're concave down. Now, with both of those pieces of information, you know basically what the function looks like. If the first derivative is positive, that means it's an increasing function. Second derivative is positive, that means it's concave up. It's got to look something like that. Okay? Got to. If the first derivative is positive, going up, but the second derivative is negative, meaning it's going down, it's got to look something like that. Okay? So you have a basic idea of how it looks. First derivative is negative, that means it's decreasing. Second derivative is positive, so it's concave up. It's got to look something like this. If the first derivative is decreasing, is negative, that means the function is decreasing. If the second derivative is also negative, that means it's concave down, so it has to be decreasing, but decreasing going down. So basically, you know the basic shape of that function. It's only the zeros that you have, and they're usually pretty good things to know, but you will not necessarily have that shape until you see the second derivative of that. And the second derivative is 0, then you might have to do a test there. But basically, this removes the necessity for test. So in graph sketching, we focus on the transition points. That's where the basic shape changes due to a sign change. Okay? A sign change is either F prime, meaning local minimum or maximum, or F double prime, points of inflection. Okay? So we're looking at those transition points. Also in graph sketching, we must pay attention to asymptotic behavior. What do we mean by asymptotic behavior? You had this back in pre-calculus, I hope. What is asymptotic behavior? Say again?
Asymptotes.
Yes, asymptote. What is an asymptote? We've got two kinds of asymptotes. What are they? Vertical and horizontal. Okay, let's deal with the vertical asymptote. What is going to make a vertical asymptote? Just about always a 0 in the denominator. If you have 0 in the denominator, you know that function cannot have a value at that. Okay? Now, of course, if you have 0 in numerator and denominator, then you do L'Hopital's rule and keep going. Okay? But if you have a 0 in the denominator, that's probably going to mean you have a vertical asymptote. Okay? The function cannot have a 0 in the denominator. That's the most common. Now, if there are others, we'll mention those as we get close. Horizontal asymptote basically is what's happening in the end behavior. What's happening in the long run as x is going to infinity, either positive or negative, is a function approaching anything there. We really don't care too much well, we do when we're sketching graphs, but that's the other thing. That is, the behavior of f of x, the asymptotic behavior, as x approaches either plus or minus infinity for a horizontal asymptote or some value that it can't have, like where x would be 0, the denominator would be 0, and that would be a vertical. Okay. Now, this is the graph that shows those transition points. Okay? Here we can look at this just by the shape here. This is sort of going backwards. Okay? If you're given the graph here and you have a transition point here, you have a graph going here, you know the first derivative is what? Say again? What did you say? I couldn't hear.
Decreasing.
There? Decreasing. Okay, I can't hear well. Decreasing, so the first derivative is negative. Okay? How about the second derivative? Just looking at the graph here. Positive, because that's concave up. So the first derivative is negative, second derivative is positive. By the way, when they put these two signs next to each other, that's what we mean, per second, okay? Over here, right here, the first derivative is 0, which means that's a critical point. First derivative being 0 or undefined, that's a critical point, okay? So that's the little red dot. Over here, first derivative is positive. You had a sign change where that's 0, so therefore that made it a local minimum, okay? And here your first derivative is positive, but your second derivative stays positive, concave up. But over here, first derivative is still positive, the second derivative has become negative, so that's being concave down. There was a transition point, and that's also called a point of inflection. Okay? This was a min or max, and here's Angelo. All right. Now, if I can't remember, I know you've turned in at least one test. Have you turned in both? Okay, I got the second one today. Okay. At the end of the class, be sure to come up and get your first test. Everybody who came in since the beginning. First of class, I return them all, but I want to interrupt class every time someone comes in. So this is a transition point because here the second derivative changes sign. We call that a point of inflection. So here we have first derivative positive, second derivative negative. Here we have first derivative 0. That could be a local extreme or not. Okay? So what we do, we look on the other side. First derivative is now negative. Second derivative is still negative because it's concave down. So therefore, this was you had a change of sign of your first derivative. That meant it was a local maximum. Positive and negative. First derivative means a local maximum. So first derivative is negative, decreasing. Second derivative is negative, concave down. Over here, though, the function's still decreasing. First derivative is still negative. But here you see, by this time, it's become concave up. So the second derivative is going positive. So here you had a change of your second derivative, another point of inflection. Okay? So your second derivative changed something. And here we have our third place where the first derivative is 0. You have a negative first derivative on one side, positive on the other side. You know that has to be a minimum. So that's another local extreme. Second derivative stays positive, stays on 1. If this was a polynomial function, after that, you know you don't have to look any further. Other functions you might have to. Those are the ones. How do we determine those? Take your derivative. First derivative, set it equal to 0, find your critical points. Okay? They may or may not be local or extreme if you use continued testing. Take your second derivative, find out if they are 0. They may or may not be points of inflection, but you do your rest of your tests to see if they are points of inflection. Okay? A critical point is a minimum or maximum if the first derivative changes sign on either side of it. A second derivative is an inflection point if the second derivative changes sign on either side of it. Okay? So that's what makes your inflection point. Okay. Now, what we didn't do is look at end behavior. Now, you did this back in pre-calculus, or at least I hope you did. The end behavior of this sure looks like it's going to positive infinity. The more negative you get here, it looks like this just keeps going up and up and up. Now, we don't have enough to say that for sure it doesn't change sign up here, but you usually can tell that looking at your derivatives. Here it looks like that's going up. So this end behavior would be going to positive infinity on the left, positive infinity on the right, so you know you're not going to have any more sign changes of your first derivative or sign changes of second derivative. You're just going to continue the way they are. Okay. If indeed that was what you had. Okay. Now, all right. Let's focus now on polynomial functions. They are so neat and reasonable. Tell me 2 characteristics of a polynomial function. There's bunches of them. Tell me 2 of them. First, what is a polynomial function? Every term, the exponent for the variable in every term is a positive whole number, period. You can't have any negative exponents in a polynomial. You can't have any fractional exponents in a polynomial. You can't have any decimal exponents in a polynomial. The exponents have to be whole numbers, positive whole numbers. Okay? Now, the largest positive whole number is called your degree of your exponents. All your exponents, we'll find the largest positive, well, they're all positive, largest exponent, that gives you the degree of the polynomial. Okay? Now, say again? I thought you said so. Okay. All right. This gives you a few examples. See if we can find the pattern here. Degree 3. Now, let's start. What would a degree 1 polynomial look like? Maximum exponent is 1. What's the graph of that look like? Straight line, exactly. That straight line is either going to have a positive slope or a negative slope. Now, to have a zero slope, that's actually a 0 degree polynomial because there is no x dependence at all. It's always a constant. So that's a 0 degree polynomial. Okay, first degree polynomial is either going to be strictly increasing or strictly decreasing. Second degree polynomial, what do they look like? Parabola. Parabola is always either opening up or opening down. Okay? Third degree polynomial, we call those cubics. Look at what it is. It's either heading downstairs here and upstairs there, or if that initial coefficient was negative, it flips it over. Towards the positive infinity on the left, negative infinity on the right. Always going in the opposite direction. Fourth degree polynomial. Okay? If that leading coefficient is positive, then it's on the up and up. A lot like a quadratic, except it's got some wiggles in between. But the end behavior looks just like this. By the way, the end behavior of a cubic function acts just like the end behavior of a linear function. Going opposite directions, either positive or negative. Same thing here, depending on the sign of that leading coefficient. And this is just like a parabola too. It's on the up and up if that leading coefficient is positive. It's on down and down if the leading coefficient is negative. Y'all remember this? Okay? And then degree 5, just like degree 3. It's going this way if that leading coefficient is positive, that way if it's negative. This tells you that leading coefficient is negative. So yeah, there's a pattern here. Yeah, in between, there's wiggles and squiggles, okay? No problem. But the end behavior always operates the same. If it has an odd degree, 1, 3, 5, 7, 9, 13, 517, 4,513,000, any odd degree, then you know the end behavior is going to be going in opposite directions. Everything then depends on what the sign of the leading coefficient is. The line of sign of the leading coefficient is positive, it's going the way you would expect. Negative, it goes the opposite way you would expect. Even degree, going in the same direction. Up and up or down and down, depending on the sign of that leading coefficient. If the leading coefficient is positive, up and up. Down, if it's negative, down and down. Okay? Every time. Works for polynomials. Now, the two things I was looking for originally when I asked you about polynomials is two characteristics of the graph of a polynomial function. Number one is continuous. Polynomials are continuous for all real numbers x. All real numbers. So when they start going in that end behavior, they just keep on climbing or keep on falling or whatever they're doing, they keep on doing it. Okay? The second thing, they're always smooth. You don't have any points, cusps, jagged corners, or anything else. Everything is smooth and continuous for all real numbers. Okay? So, is this example 1? I think it is, but let's see. Yeah, I believe it is. Okay. So, whoa, get back there. Okay. So let's do example 1. Sketch the graph of the polynomial of the function f of x is equal to x squared minus 4x plus 3. Okay, if you're going to sketch the graph of that, what would be a first thing to note? I mean, you can note them in any order you want to. Let's just take one. What kind of function is it? Second? You probably said it right, I just don't hear well. It's second degree. What does that tell you? It's going to be a parabola. The graph will be a parabola. Okay? Is there anything else you can tell without drawing a single thing on it? Which direction is going for its end behavior? Up and up. Because the leading coefficient is positive and you have an even exponent. It's going to be up and up. So before you draw the graph, you can write down the end behavior. Okay? So if this is going to be my graph over here, I know it's going up here and up there. Okay? Now, let's go back to Math 100 or somewhere. What would you have done first if you're going to graph that function? Factor it. Sounds like a capital idea. So first we deal with the function itself and factor that if it's factorable. Is it? And how does that factor? X minus 3 times x minus 1. And what do we do with that factor? Set it equal to 0. What does that tell you? So x equal 3 and x equal 1 are the zeros of this function. So there's 1 and there's x equal 3. There's 3, I'm sorry. X equal 3, okay? You have a 0 there, you have a 0 there. Okay? So, first thing you do, look at the function, to do end behavior, we did it. Then, see if you can find the zeros of the function. Okay? They're just nice things to know if you're going to graph. There is one other thing. What are these zeros of the function called? They're also called a different name. What is another word for it? Think football. The defensive back steps in front of the receiver. Intercept. Okay, go intercept. And yeah, these are called x-intercepts because the x-axis intercepts the ball. No, the function. That's where it crosses. So that's something. So we have the x-intercepts. Is there maybe something else? What? Another kind of? A y-intercept. How many of those do you think we could have? Really? We have 2 y-intercepts. Guess what? That's not anymore. It's not a function, is it? It can only have 1. And since this is a polynomial function, smooth and continuous for all real numbers, it's got to cross that y-axis somewhere. That's going to be the y-intercept. How in the world do we determine what that is? Say again? That won't give us a y-intercept. It's even easier than that. You did it before you knew how to take a derivative. How do we get the x-intercepts? We set, what is f of x always? Y. We set y equals 0. So guess how we get the y-intercept? Set x equals 0. Set x equals 0, what's the y-intercept? 3. Okay, so we have another value. Y equals 3. So there is a point. So there we got our intercepts. Very good. Now, what were you hankering to do? Take a derivative. F prime of x is equal to what? 2x, so I got minus 4. And guess what we're going to do to it? Set it equal to 0. Very good. And what does that tell you? X equal 2. Very good. What does that tell us? What is that x equal to? We have a special name for it. It's a CP. Critical point, critical value I like to call it. It's our critical value, okay? And what's that going to tell you? Where you're, potentially where you have a max or min, an extremum, okay? Now we know already, you already told me it's a parabola, okay? And because we know the leading coefficient is positive, we know it's on the up and up. So this has got to be a minimum. So, well, we'd see that already. X equal 2 is going to be a minimum. So what we can do is plug this back into our function and figure out what f of 2 is. That's going to be our minimum value. What would that be? What would it be? There's your f. Plug in 2. 4 minus 8 plus 3. And what does that give us? Second? 7. Okay. I don't know the new math. What does it give in the old math? Okay. Huh?
-1.
-1. Okay. That's the one I recognize. -1. All right. Oh boy, maybe we should go back somewhere here. -1. Okay. Now, we have found, and we know since it's a, well, I want to say more, but I won't. We know that it's on the up and up, so I know right now that is what kind of point it is. Without doing anything else, I can tell you that is a, because see, here it's positive, here it's greater, so that has to be a minimum point. So, now, that is also another thing, since this is a parabola. Now, this only works for parabola. That is also called a, anyone know what we called that? AOS. Axis of symmetry, exactly. And you notice these 2 points are symmetrical about that, and I could tell you right now that you're going to have another point right here symmetrical to it. Couldn't you? Because of its symmetry there. Okay? So, all right. So this point was 2, -1. Okay? That's the minimum point. Here's going to be confirmation of this. It's almost extraneous now. Let's do we've done the first derivative. What else could we do? Help me. We did the first derivative. What else could we do? What would follow a first derivative? A second derivative. So let's do f double prime of x. And what would that be? Looking at f prime of x, 2. Now what does that tell you? What does that tell you? First, what's the sign of 2? Positive. Very good. What does a positive second derivative tell you? Say again? Concave up. Concave up. This is concave up everywhere. Okay, how do I know that? What would be a point of inflection? Where the second derivative was 0. And can 2 ever be 0? Is that 0? No, it can't. Can't ever be 0. So this has no points of inflection. It has one critical value, x equal 2. That turns out to be a minimum where y is equal to -1. and it's a parabola, and it's going on the up and up, so everything fits fantastically. Okay? Now that was a pretty simple one. Okay? But you see how your first and second derivatives help you. So what we have here, the first derivative was, we found where the first derivative was 0, that's at x equal 2. Now they did a sample and did, what is it at x equal 1? Okay? If you looked at that, the first derivative was negative. We didn't do that. We didn't plug it in. You could have done that. Plug in a 1 here, and that would give you 2 minus 4 is negative 2. That meant the first derivative was negative everywhere to the left of 2, 0 at 2, and then pick one to the right. Well, how about 3? First derivative would have been 2 there. So that means it's positive from there on. So what this tells us that between negative infinity and 2, the first derivative is negative, and between 2 and positive infinity, the first derivative is positive. So that meant at x equal 2, it was a minimum. That was your critical value, x equal 2. Critical point was 2, negative 1. And the second derivative was positive everywhere, meaning it's concave up everywhere, had no inflection points. Does that make sense? So you can tell tremendous amount of information about the shape of a graph, how it looks, just by taking your derivatives and evaluating, analyzing. Okay, so let's go on to a cubic polynomial. Okay, there's the graph. We've already done it. There's our y-intercept. They didn't tell you to do it, but we found that. X-intercepts, local minimum at 2, negative 1. Yep. Concave up everywhere. Second derivative positive everywhere. First derivative negative up till 2. Negative infinity to 2. Positive from 2 to positive infinity. Okay. Any questions? I probably should have blown that up. Everything I just said. Okay? On the up and up. So let's now look at a cubic polynomial. Okay? Let's sketch the graph of this one. F of x is equal to 1/3 x cubed minus 1/2 x squared minus 2x plus 3. Okay. My question to you, what kind of function is this? It's a cubic what? Polynomial. Cubic polynomial. That's what they said, cubic polynomial. I said it earlier. Okay. Wait a minute. Can that be a polynomial? Why not? What's not a whole number? The what? Okay. Okay. Now there's where what makes it a polynomial, the exponents are all whole numbers. 3, 2, 1, 0. All those are whole numbers. The coefficients can be anything. They could be fractions, decimal, rational, irrational. Square root of 17 could be a coefficient. Can't be an exponent, but it could be a coefficient. So no, this is still a polynomial function. It's only the exponents that have to be whole numbers, not the coefficients. So this is indeed a cubic polynomial. Cubic because the maximum exponent is 3. Polynomial because all the exponents are whole numbers, and it doesn't matter really what the coefficients are. To some extent, there are some things we do avoid, like complex coefficients. We don't use those. Okay. All right. Now, what was the first thing we did on the last? Well, okay, yeah. What's one of the first things we probably need to do with this one? Determine its end behavior. Okay? How do we determine its end behavior? Two things we look at. And they're all in one term. I call it the leading term test. In our pre-calculus text, it calls it the leading coefficient test. No, it's a leading term test. It's called the leading term. Which is the leading term there? Say again? No, that's the leading coefficient. Okay, but that is in the leading term. The leading term is not always the first term. Okay? You can scramble these terms. This leading term is always going to be the one with the maximum coefficient. That's the leading term. Okay? And the leading coefficient is 1/3. What's important about that? The major thing that's important about it. Its sign. The value of it is sort of important, but the major thing is the sign of that. And what's important about, what's the other number in that leading term? That's the coefficient. The cube, that's the exponent. What do we look for there? Not the sign, because with a polynomial, it's always going to be positive. But what do we look for? Even or oddness, which is this, which tells you what? For end behavior. They're going in the opposite direction. If it's an odd exponent, the end behavior is the opposite direction. Now we go back to that leading coefficient, what we're interested in there. The sign, okay? If that's a positive sign, then negative x's go to negative y's. Positive x's go to positive y's, okay? If that was a negative sign in front, negative 1/3, then a negative x goes to a positive y, and a positive x goes to a negative y, because they're always going to be opposite directions. So since this is an odd exponent, they're going in opposite directions. Positive coefficient, that means negative, negative, positive, positive. Okay. So we got the end behavior. Okay. Sketch the graph. So let's draw our graph here. It's going positive this way, negative this way. Okay? That doesn't tell us much, but it tells us something. Now, anyone particularly interested in factoring that? It really isn't quite as bad as maybe it appears. What would we do? Why do we factor anyway? We're looking for the zeros. So let's see if we can do that. Just set it equal to 0. And then what I want to do is, what would you want to do? What is messy about that? The fractions. So how can we get rid of them? What do we usually do with fractions? Quite often, not always. Find their common denominator. What's the least common denominator between 2 and 3? 6. So let's multiply this whole thing by 6, okay? It's a different function, but I don't care. It's going to have the same zeros. So this will become 2x cubed minus, help me. Multiplying the whole thing by 6. 3x squared minus 12x plus 18, okay, equals 0. Okay, now, I don't know if this is going to work, but let's give it a shot. The only way I know how to factor a 4-term polynomial is grouping. Okay, let's give it a shot, see what we get. Anything you can factor out of that first group? More than that. X squared. And what are you left with? Two x minus 3. How about the second group? Anything you can factor out there? Better? Okay, one thing else. Take out the minus sign too. Minus 6. What do you have left? You hold out the minus sign. 2x. You pulled out minus 3. See why I pulled it out? That's equal to 0. Hey, what do we have now? Common factor. So what do we do? Pull it out. 2x minus 3. And what do we have left? X squared minus 6. That's equal to 0. Okay? Now, I know what this gives us. What do we do with that? Okay, you set it equal to 0 because all these factors have to multiply to 0. One of them's got to be 0, at least one. So 2x minus 3 equals 0. And then add the 3 to both sides, and that gives you 2x is equal to 3. That means x is equal to 3 halves. So there's 1, 2, 3, 4, 5, 6, 7, 8. Negative 1, 2, 3, 4, 5, 6, 7, 8. Positive 1, 2, 3, 4, 5, 6. Negative 1, 2, 3, 4, 5. Okay. So 3 halves, x equals 3 halves is right there. Okay? And that's a 0. So we got it in the right place. Now, what's the other factor here? X squared minus 6 can equal to 0. Uh-oh, that's a little messier. But we could still add 6 to both sides, and you get x squared is equal to 6, right? And then what could you do? What could you do? Take a square root, and that would give you x equal, almost right, one is half right. Anytime you take the square root of both sides, it's a plus or minus root 6. Root 6 goes through intelligent. No, I'm just kidding. Okay, now what is square root of 6? Approximately. Just give me a raw figure. Between what two numbers? What's root 4? What's root 9? It's between 2 and 3, isn't it? So let's just say, yeah, what, you punched it in, what'd you get? 2.3 or 4? 2.44. Okay, let's just call it 2.4. 2.4 is going to be somewhere about there, and minus 2.4 is going to be somewhere about there. So here are our other 2 points. I can't do a 4 on that line. I can't even come close to it. There are 3 zeros. Fantastic. Okay? Now what could we do? What are these 3 points called? Zeros. That's what we were calling. There's one other name for it. X-intercept. So what else might we try to find? Y-intercept. How would we find the y-intercept? So x equals 0. If x equals 0, that's 0, that's 0, that's 0. So what is y? 3. Okay. Height. Okay. So 3 is, again, our y-intercept. It's not always, just these 2 examples it is. So now we've got our end behavior, we have our zeros, and we have our y-intercept. Now what would you do to that function? Okay, I'm going to erase some of this just because it's in the way. Okay, like we don't need that anymore, and we don't need that anymore. We've already dealt with that. So what's another thing we could do to this function? One of those questions. Take a derivative. So what? Ooh, let me get my pen back. F prime of x is equal to help me. X squared minus x minus 3. Or 2, you said, right? I can't hear well. Okay? Now, what might we do with that? Okay? The reason we factor is because we set it equal to 0. Why do we want to set it equal to 0? First derivative equals 0 will be our critical values, okay? And so let's factor it. And how does that factor? Does it factor? Does it factor? How? I know it's an x and an x. I know it's a plus and a minus. One and a 2. Buckle my shoe. Okay, what does that give us? Either x equal -1 or x equal 2. And those are our critical values, which could be, and in this case will be, local extrema. Okay, but we don't know which is which. Okay, so x equal -1, there it is. We need to probably plug that in here. Okay, so let's go back to our function. F of -1 would then be what? It's not that hard to do. Plug it in, plug it in. -1 cubed. -1 times what 1/3 is? -1/3. Is this going to be a plus or a minus sign? Because you're squaring it. That's -1 squared is 1. So that stays a -1/2. Okay? And then plus 2. The rest won't do. Okay? Oh, wait. No, yeah, we do need the plus 3. Okay. All right. So here we're subtracting off. This will be minus, okay, I got to get it to 6, right? This will be -2/6, and this will be -3/6. Okay, so that's -5/6. 5 minus 5/6 would be 4 and 1/6. So there's your F of -1. Right there is going to be plus 4 and 5/6, almost up to 5. Okay, right there. Okay, let's do the 2. F of 2. Ew, this is even worse. 2 cubed is? 2 cubed is? So that'd be 8/3 minus 2 squared is? Half of 4 is? 2, so that's not going to be too bad. -2 times 2 is? -4 plus 3. Okay, so that's going to be -6 plus 3 is -2. No, wait, -3. Yeah, -3, and then 8/3 is 2 2/3. So plus 2 2/3. -3 plus 2 2/3 is -1/3, right? So at x equal 2, you're -1/3, right down there. Whew, not very big at all. But I think we got our shape of our function here. It's got to be going down here. There's our maximum. Has to go through that one, down here. There's our minimum, and go on up. Now this should be a lot smoother than what I drew it. Okay, all right. That looks like the function now, and we haven't even done the rest of it. Okay, just looking at the points, connecting the dots, that gives it to us. Let's go on and do, what would we do next to confirm this? Yeah, let's take our second derivative. So f double prime of x is going to be what? Here's f prime. F double prime is going to be 2x minus 1. And guess what we're going to do to that one? Set it equal to 0. And then we're going to do what? What did we do every time before? Solve for x, yes. Add 1. So that gives you 2x equal 1. X equal 1/2. What's that going to be? They had a name for it. I think they called it a transition point. Okay? Okay. Notice the pattern, folks. You take your function, set it equal to 0, see if you can solve and find your x's. They'll give you your zeros or your x-intercepts. Then while we're there, go on and do the y-intercepts. It's so easy. Then take your first derivative. Set it equal to 0. This time you're finding critical values. Okay? And when you find those, plug those in. Then take your second derivative. Set it equals 0. That gives you transition points. Okay? And that happens to be x equal 1/2. That's a transition point right here. And it's got to be on the thing. And they've been drawing these as squares. Okay? And what do you think that's going to mean? Just looking at even my ugly graph here, this looks like it's second. That's not a local minimum or maximum. That's going to be your critical values give you that. Your transition points give you your points of inflection. And what is it on this side of that point of inflection? Your second derivative? Second? Down, it's concave down, meaning the second derivative is negative. Okay? And where your over on the right side of that transition point, what does it appear? Concave up, which means the second derivative is positive. Oh, we got it. Okay. So there we have everything we need. Okay? The only thing we didn't do was test that to the left and right. It's real easy to test when x equals 0. That's left of 1/2. That's going to be -1. Sure enough, concave down there. And to the right of that, let's do x equal 1. 2 minus 1 is 1. So it's positive there, concave up. Sure enough, there is our transition point. You got your zeros, which are your x-intercept. The y-intercept was easy. Then you did your critical points or critical values, where your first derivative was first derivative was 0. Plot those, and then second derivative, where it is 0, that's going to be your transition point. And the first derivative equals 0. Your critical values, you're testing to see if you change signs of your first derivative. We did. You could tell by the dots you had to. Okay? Then the second derivative, you can tell by the shape of the curve you have. You had to have a change of sign there. So indeed, that was an inflection point. Make sense? Okay. Now they go and do a bunch of tables. So let me erase. Okay. They did the interval from -infinity up to -1. The first derivative was positive there. Okay? And first derivative was positive. From -1 to 2, your first derivative was negative. From 2 to positive infinity, your first derivative was positive. So just check it. Sure enough, that's what we found. We knew that from our end behavior. We knew it from lots of places. Okay? Then our second derivative from -infinity to 1/2, going back to that, second derivative was 0 at 1/2, -infinity to 1/2, second derivative was negative, and from 1/2 to positive infinity, it was positive. So concave down, concave up, that made 1/2 at point of inflection. Okay? So you don't have to draw tables, just note them, as you go. Does that make sense? It makes plotting graphs pretty easy. Now, that one happened to be one that you could factor that cubic. You can't always do that. So you may not have had your zeros to begin with, so you have to just do with the rest of it. Okay? and here are your various sign combinations. To me, this is just redundant because we've already determined everything here. But here's what we found out. Your critical values, well, you found your zeros, was it whatever they were. 3 halves, we had 1. Plus or minus the square root of 6, which is 2.4 minus 2.4, you had 0. They didn't do those. Those are pretty easy to do. Y-intercept, even easier. Do it. This helps you out, okay? Then your first derivatives, where those were zeros, they gave you critical values, -1 and 2. And then you can test those by doing your first derivative to the left and right of those, left and right of those, and you see you do change signs for first derivative, you change signs for first derivative, so that's local min, local max, local max, local min. In behavior we had already done, they didn't show that, that's really easy to do. And then you did your second derivative, so you were there, that was a transition point, we tested the second derivative was negative to the left, positive to the right, so therefore that was a inflection point there, okay? Concave down to the left, concave up to the right. You can do this if you want to. Basically, if you're plotting your points, you've already done it, okay? So, boy, can they ever make it complicated, okay? So you did your critical value, we'll know with x equals -1, x equals +2. We came up with 4 and I don't remember, we got 4 and 1/6. So I thought it was a little less than 4, so I may have messed that up. But we still got in the same ballpark. And then this was 2 -1/3. I think that one was right. Y-intercept was there. They didn't show how to get it, but it was so easy to do. Your zeros, we had already done those, or at least approximately. And then when you add your shapes to it, concave down, concave down, concave down, concave up, yeah, you got it. Do we do all that? No, you just do that once, okay? Knowing you have the transition point at 1/2. Okay. I should have blown that up on the guess. Okay. Whoa. Can't quite get it all in, but I can get most of it. All it left off was my x-axis. Okay. Oh man. Is this a different one? I think it is. Yeah, I think this is example 3. I know someone right in the middle of that one needed to get up. Do we need to take a quick break? At least stretch? Restroom if you need to? Yay or nay? Yay? Okay. Let's take a real quick break. Okay, I think this is the next problem. This is example 3. Sketch the graph of this one. F of x is equal to 3x to the 4th minus ax cubed plus 6x squared plus 1. Okay. It says sketch the graph. Now, what have we done the first two? What was our first step? The 2 previous ones. What did we do before? Second? Okay, yeah. Let's start there. What is your end behavior? Positive to the left. Positive to the right. Stand up, sit down, fight, fight, fight. Okay, so let's do our graph here. We know it's on the up and up. Okay, we know it's going up in both directions. Why? What told us that? Yeah, the maximum degree is 4. That's even. That's on the same direction. The maximum exponent, the leading coefficient was positive. So that means something up and up. Okay. So we did determine that. That's a good thing to do. Now, what's the next thing we did before I don't think we can do here? Or if we do, it's going to take a little more work. What was that? Before we set it equal to 0, didn't we? And tried to find our zeros for the function. And we were the last two times, one by factoring, by grouping, the other was just a simple quadratic, which is easy to do. This one, number one, is a quartic function, degree 4. It has an even number of terms, but we're missing a term, the x term, that would have an odd number of terms. So factoring by grouping never can be done with an odd number of terms. And this one, to do it, you'd have to put in a 0x, and you couldn't do it then. Now, I don't know if you recall back from your pre-calculus when you did things like rational zeros test. Remember that? Does that ring a bell? No. Okay. Too bad. Okay. Let me just give you the quick and dirty on it. You look at the last term, the constant term, and the leading coefficient. The ratio of those, last over first. 1 to 3. And you do all the possible factorizations of that. Plus or minus 1 is all you got for the numerator. Plus or minus 1 and plus or minus 3 is all you got for your denominator. Now, all you can get out of that is plus or minus 1 and plus or minus 1/3. That's all she wrote, okay? Let's do the plus 1. That one's so easy. Let's see if that's a possible 0. What would that be doing? Adding your coefficients. So let's do it. 3 and 6 is 9 and 1 is 10, and minus 8 is not 0. So that one will not work. If you put a minus 1 in for the x, this will stay a 3. That will become a plus 8, right? And that would be stay a plus this, and that will, yeah, that's definitely not going to be 0. In fact, it's always positive, okay? In fact, what that tells you, nothing beyond, I'm sorry, that was a negative one. So that's not going to work, okay? Actually, anything beyond minus 1 is going to keep climbing, so we're not going to mess with that. You could go in and try your 1/3 and do synthetic division, and then do minus 1/3 and do synthetic division with that. You might find a 0 that way. I'm really not wanting to take the time to do that, okay? You could. Do you remember how to do that? Want me to do it quickly? It's not that bad. Remember I said our rational zeros were plus or minus 1 over plus or minus 3, all the possible factors there. Plus or minus 1, we already said they aren't going to work, so the other is plus or minus 1/3. So let's do a plus 1/3. Synthetic division, plus 1/3. Put 1/3 on the outside, okay, and then put your coefficients on the inside. 3, -8, 6, 0, 1. You have to account for every term. Now, my little trick to check and make sure I've got enough, count the number of numbers you have. 5, it always has to be one more than the maximum exponent. It is, so we're done, okay? Skip a line, draw a line, okay? Bring down the 3. Multiply. 1/3 times 3, 1. Add, -7. That would be -7/3. Add. Well, this will be 18/3 minus 7/3. Goodness gracious. 18/3 minus 7/3. That would be 11/3. Multiply, and that would be 11. Add, you get 11. And then you get 11/3. That doesn't give you a 0. Okay? So 1/3 isn't going to work. Okay? Let's try minus 1/3. Okay? I don't think it will either, but we'll give it a shot. Okay? We'll do a minus 1/3. Minus 1/3 times 3 is minus 1. This gives us a minus 9. That's looking better. That gives us a plus 3. That gives us a plus 9. That gives us a minus 3. That gives us a minus 3. And that gives us a plus 1. Oh man, so close, but not a 0. Okay? But you have a pattern here. Plus, minus, plus, minus, plus. That came up with 2. When you have a pattern like that with a negative, you know that don't go any further than minus 1/3. It's not going to work. Well, what does that tell us? Either we have no zeros, or you just have no rational zeros. Okay? Now there's another little test there. I don't know if you remember that. Does Descartes' rule of signs ring a bell? Ding, way in the back, but you can't make it out. Yeah. Descartes' rule of signs, you look at the number of sign changes. Plus, minus, plus, plus. That's 1 sign change, 2 sign change. That means you either have 2 or 0 positive real roots. Well, that doesn't tell you a lot. You could have 2 or you could have none. We don't know which. Now, to get the negative real roots, you do f of minus x. And that would be, when you put a minus x in for x, since you're raising it to even power, that's still 3x squared. A fourth, I'm sorry. But this one changes sign because your minus x cubed would be a minus x cubed times a minus 8 would be a plus 8x cubed. And minus x squared stays at x squared, so that's a plus 6x squared plus 1. You have no changes of sign. That means you have no negative real roots. Okay, and Jasmine's here. All right, is anyone else come in since we called roll? Okay, now, I ask everyone who's come in, if you've turned in either of the first 2 tests, I'll give them back to you at the end of the class. If you haven't turned them in, please turn them in, as soon as possible, because you've got to have them in today. Okay, so we have no negative real roots. Here we knew we didn't have any negative real roots past negative 1/3. Descartes' rule of sign says you have no negative real roots. So you could have 2 positive real roots, or you could have none. So far, we haven't been able to eliminate anything. So your roots didn't get you anything. Setting it equal to 0 got you nothing. Worth a shot, because sometimes it'll work, but this got us nothing. Whoops, I just erased our end behavior. I shouldn't have done that. But all that analysis got us not much further than we were when we started. We just know we have no negative real roots, and we could have 2 or none positive real roots. Okay? And I erased way too much. Okay. We know we have end behavior here and end behavior there. Okay. So where would we go next? All that effort got us very little. What do we do next? Help me, help me. Take a derivative. Good idea in a calculus course, okay? F prime of x is equal to 12x cubed. Is that right? I can't hear you, okay? Next. Minus 24x second. Is that what you said? Okay. Plus 12x. And what do we do with that first derivative? Set it equal to 0. And then what do we do? Factor. And what can you factor out here? 12x. And what do you have left? Now here x squared minus 2x plus 1. Right? Oh yeah, okay. Equals 0. Now what does this tell you? Say again? What does that tell you? Does it tell you anything? What do you do with that? Okay, yeah. So either 12x is equal to 0, which would yield what? What? X equals 0, okay? That tells you something. At x equals 0, you have a potential maximum or minimum, okay? And what else does it tell you? X squared minus 2x plus 1 equals 0. Well, what can we do with that? Factor again, and what does that give us? X minus 1 squared is equal to 0, right? That's a perfect square trinomial. So this gives us only one 0, x equal 1. It's a double 0 though, okay? Meaning that at x equal 1, well, the first derivative, okay. So x equals 0, we've got a critical value, and at x equal 1, you have a critical value, okay? So let's plug them into our original thing. X equals 0, and we should have done this anyway. What does that give you? Where x is equal to 0? Alpha 0? 1. Okay, that was our y-intercept. We couldn't find the x-intercept. We could have found the y-intercept. That is also a critical value. Okay, x equal 1 is also going to be a critical value. So what is alpha of 1? We already did it when we added our coefficients. 3 minus 8 plus 6 plus 1. Okay, and that's going to be positive 2, isn't it? So x equal 2. Okay, there are our two critical values, the only two critical values. Okay, now I am pretty certain this one's got to be a minimum, don't you think? If it's going up, remember our end behavior, and it's going up here, that pretty much got to be. Now, this is just a rough analysis. If it's going up here and it can't come back down without going up again, or give us another critical value, I think what happens here, we must have a point of inflection. I'm guessing that's what that function looks like. Okay? And guess what? Sure enough, Descartes' rule of sign says you had no negative real roots and either 2 or no positive real roots. No wonder we couldn't find the 0. It doesn't have any, or it doesn't look like it does. We're going to still do some more analysis on it later. But let's do. So far, that tells me it's got to look something like this. Let's do some more analysis. What's the next thing you would do after you do first derivatives? Second derivative, okay? I think I'm going to erase some of this just because it is sort of messy and in the way. We've already done our calculations with it, so that's done. You can keep it on your piece of paper. I just have a very limited amount of room to work here. So let's clear the space. Whoa, I erased my curve. Okay. All right. Let me get that part back in. We think this is on the up and up here. Okay. So let's do our second derivative. F double prime of x. What would that be? 36x what? Squared? Yeah, it's to the second. Okay, next. 48x plus 12. Okay, and what would be what you want to do with that? Set it equal to 0. That's what we do. We find the function, either the function set at 0, mess with it. First derivative set it equal to 0, mess with it. Second derivative set it equal to 0, mess with it. Okay, let's mess with it. So the next thing we do, it's your F word, factor. And what can you factor out of every one of those terms? A 12. And what does that leave you with? Help me, help me. 3x squared minus 4x plus 1. Okay, and that's equal to 0. Now, question, can 12 ever be equal to 0? No, of course not. So we'll divide out the 12. It's out of there. Okay? So let's do the rest of it. Can that ever be equal to 0? Well, it looks like you might be able to factor that. What's the only possible factorization for 3x squared? 3x times x. Okay? Now, where do we look next? The sign of the last term. What is that? Sign of the last term. Positive. What does that tell you about these two signs? No, they got to be the same. Okay? So you look at the middle term, and what's that sign? Negative. That means they both got to be negative. What's the only possible factorization for 1? 1 times 1. Let's see if this works. It may not. 3x times x is 3x squared. Fantastic. 3x times minus 1 is? 3x times minus 1 is? Negative 3x. Negative x would be negative 4x. Bingo. Oh, can't say that now, though. And then minus 1 times minus 1 is plus 1. Sure enough, that is the proper factorization. What does that tell us? What do we do with that? Since we got the proper factorization, what? Okay. Say what you said. Set each of them equals 0. So 3x minus 1 equals 0, or x minus 1 equals 0. Very good. What does the first one give us? Say again? X equal 1/3. Is that what you said? Yeah, that's right. And the other one? X equal 1. Okay? Now those aren't zeros. Those are where your second derivative are equal to 0. Okay? Now what does that mean? Those are your transition point. Oh, no, they call them something else. What do they call them? Yeah, transition points. Is that a point of transition or not? Let's investigate to see. X equal 1/3. That would be right about here. Okay, so it'd be right here. Yeah, you know what? It sure looks like it's concave up before there. You can test that by putting a 0 in. I think you'll get that to work. If you put a 0 in here, you get positive. So yeah, that's going to work. Concave up there. And it looks to me like it's concave down there. And then x equal 1, it's concave down here, but concave up there. So that's another point of transition. Okay? Point of inflection. You have an inflection point here and an inflection point here. That's both. Okay, now let me do something else. Give me another color. Yellow. Okay? Okay. I'll put a yellow box, meaning it's a transition point, What did you say? Did you not say yellow? Oh, okay. And then I'll put a dark dot in the middle of it. That means it was the first derivative equals 0, meant it was a critical point, but then he also had second derivative equals 0 at the same point, and that meant it was a transition point. And sure enough, it wasn't a local minimum or maximum, but it was a point of transit of inflection. You have another inflection point here, concave up, concave down, concave up. So both of these are points of inflection, but one of them happens to sit on your critical value as well, which meant it wasn't a local minimum or maximum, but it happened to be a point of inflection. Okay, we've got that without doing any of the other analysis they did. We've sketched the graph. It looks like it fits. So from negative infinity to 0, your first derivative is negative. Okay? Your second derivative, they didn't say this, but your second derivative was positive because it's concave up. You could plug these in and see. From 0 to 1, your first derivative happened to be positive. And from 1 to infinity, your first derivative was still positive. Okay? From 0 to 1/3, your inflection point, your second derivative was positive. From 1/3 to 1, your second transition point, it was concave down, so it was the negative second derivative, and from there to positive infinity, concave up, positive second derivative, concave up. So you see, this is how you analyze the curve. Plug it in, see what it's at. Okay? Does that make sense? Your end behavior is going right where it's supposed to. Any question on that? Now here they do all these things, and if these are helpful to you, by all means do them. I'm not trying to make fun of them or anything. If they're helpful to you, do them. Okay? What we have from negative infinity to 0, you have first derivative is negative, second derivative is positive. From 0 to 1/3, this is your critical value, this is a transition value, and that was a critical value. So do all your graph here. First derivative is negative, second derivative is positive, so it's decreasing, concave up. At this point, it goes to first derivative positive, second derivative stays positive, concave up. So that meant this was a local minimum because you had a change of sign of the first derivative, and your second derivative meant you're still concave up there. But at 1/3, your first derivative is positive, first derivative on the right hand side is still positive, so you didn't have a change of first derivatives, but your second derivative did change sign from a positive to negative, meaning a point of inflection. Meaning concave up, concave down at 1/3, all the way up to 1, and your first derivative stayed positive, second derivative went negative, and then at 1, first derivative stayed positive, but the second derivative change sign meant that it wasn't a local maximum or minimum, it was an inflection point because your second derivative did change sign. Concave down on this side, up on that side. Okay, does that make sense? And now they piece the pieces of the graph together. Boy, they string this out no end here, but it's fine. If this helps you see it, go for it. Do it. Okay? You had end behavior, you had critical values, transition values. They just don't show the critical value there. Should be a red circle inside the green square. And so you knew you were decreasing here, increasing here. First derivative or second derivative is positive here because it had to be concave up. Here it went to concave down, but here it didn't change first derivative, so it continued going up. So this just was a point of inflection. Okay. They didn't draw the pieces in here, but they still fit. There they are. Now, I think this is the next one. Yeah, because it's a trig function. They have pies, fractional pies, so it must be trig. Sketch this one. F of x is equal to, there it is, I lost it, cosine x plus 1/2 x on the interval 0 to pi. Okay. Okay. Now, again, what you could try is to set that equal to 0. And if you try to set it equal to 0, let's get your zeros for the function, which would be your x-intercepts. And that's not going to give you very much of interest, I don't think, okay? Basically, you would have negative 1/2 x equal cosine x, or cosine x equal negative 1/2, or whatever. And then, you know, that's a very difficult thing to try to solve. But what you can do is find the y-intercept. Remember, those are usually pretty easy. How do we get it? Y-intercept? Set equal to 0, okay? And what is it when cosine x equals 0? When x equals 0, what's cosine x? Cosine of 0. 1, okay? And then when x equals 0, 1/2 x is equal to 0. So you're starting at 1, okay? So we're sketching the graph, I think. Yep. So at x equal 1, we're 1. Okay, we know that. But this was a dumb graph. Okay, let me start that over again. Oh, I didn't mean that. Yuck. Okay, never mind. F of x is equal to cosine x plus 1/2 x, right? On 0 to pi. So really, when I draw my graph, I'm really only interested in 0 to pi. Okay? And we'll put this as 1. Okay? And at x equals 0, we're at 1. Now, why not, since we have an endpoint, what happens when x is equal to pi? What's cosine of pi? First thing we did was alpha of 0, and we found that to be 1. So what's cosine alpha pi? It's cosine of pi. Negative 1. Is that what you got? Okay. So this would be negative 1 plus pi halves. Okay? Pi halves is a little bit more than 1.5, right? 3 halves. A little bit more than 3 halves. So this will be a little bit more than 1/2. So it'll be something about here. Okay? So we got 2 points on there. We didn't have to do that, but we did. Okay? And that's about all we can get now. We don't even know if it does have an x-intercept. It's going to be hard to see. So what might be the next thing we do? If setting that function equals 0 doesn't help us much, what might we do? Take a derivative. F prime of x would then be what? Negative sine, okay, negative sine x plus 1/2, Okay? And then what were we going to do with that? Set it equal to 0. Now, that's not going to be too hard to do. Let's rewrite this as sine x is equal to 1/2. Right? Because we just added sine x to both sides, so that gave us sine x is equal to 1/2. What values of x between 0 and pi make sine x equal 1/2? X equal pi over 6. Is that the only point in between 0 and pi where it's 1? 1/2. So I get 5 pi 6. 5, 6 pi. So if that's pi, that would be pi over 2. This will be pi over 4 would be there. That would be 1/3 pi, 2/3 pi, 1/3 pi, 2/3 pi. So it would be here. This will be a critical point, and this will be a critical point. Okay? So let's plug in and see what values they are. F of pi 6. What would that be? Plugging in up here. What's cosine of pi 6? Root 3 over 2 plus pi 12ths. Right? I don't know what that is. You can plug it in your calculator if you want to. I do know it's positive. Right? Okay? Someone give me a value. Root 3 over 2 plus pi 12ths. Pi 12ths is going to be something close to 1/4. Square root of 3. 2 times root 3. What's that going to be? Someone plug it in. Pi square root of 3 over 2 plus pi 12ths. Give me an approximate value. Say again? 1.12. 1.12. I'm going to say it's somewhere about like that. Okay? Now let's do this other one. F of 5, 6 pi. Okay, goodness, I can hardly breathe again. Let's plug that in. What's cosine of 5, 6 pi? Cosine of 5, 6 pi? Negative root 3 over 2, right? Okay? And then this will be plus 1/2 of 5, 6 pi. That would be 5 pi over 12. Okay, someone pull out your handy dandy calculator and see what that one is. Negative root 3 over 2 plus 5 pi over 12. Second? 0.44. That would be somewhere about like there. Because that was about 0.5 if my memory's right. It's been so long. Okay. Looks like there's our local maximum. And there's the local minimum. And you come back up there. Okay? So sure enough, it didn't have any zeros. We couldn't detect any. And it looks like it doesn't. Okay? What's another thing we can do to check other points of interest? Second, take a second derivative. You're absolutely right. If I can get this to erase without hitting the wrong key. So, sorry, I have to have enough room to write. Have to do this. So let's do our second derivative here. F double prime of x would equal what? Negative cosine x. Done, right? And set that equal to 0. Now, where in between 0 and pi is negative cosine x equal to 0? At pi halves. Okay, so sure enough, and this I think is the only place it is. So what we have then is only one inflection point, and there it is. And we can check it. Sure enough, that's concave down here and concave up there, so there's the point where it changes. Does that make sense? All right, good deal. Now, you can do a lot of other things with it. From 0 to pi 6, your first derivative is positive, okay? From pi 6 to 5 pi 6, your first derivative is negative, okay? And from pi 6 to 5 pi 6 pi is positive again, okay? Your second derivative, and we didn't check this, but we looked at the only way the graph could be, and that's all it was, from 0 to pi halves is concave down, second derivative is negative, and from pi halves to pi, it was concave up, everywhere along the way. Okay. So that gives it to us. Let's see how their graph looks. Oh man, they almost are as pretty as ours, isn't it? Okay. Now, notice the other thing they did, and it's the same thing I did too. I don't know why this thing's not showing. There we go. Okay. Okay. They put some other values in here, but they did the endpoints, and that's usually a good idea to do. Put it what it is since this is only defined from 0 to pi, figure out what it is at those two values, okay? Then when you draw your other points, you can see if they're going up or going down, that kind of stuff. Your critical points were at these two, pi 6 and 5 pi 6, and here, plug in the values here, and you see this, sure enough, it looks like it's going to be a maximum. This, sure enough, looks like it's got to be a minimum. It's a smooth continuous function. Do the second derivative at a equals to 0, that's pi x equals pi halves. That's going to be your transition point where it goes from being concave down here to concave up there. Wonderful question. Okay, any questions on that? Getting hard to breathe again. Sorry. I think they have another one. Function involving e to the x. Let's sketch the graph of this one. F of x is equal to x e to the x. Okay? And this is good everywhere it appears. Okay? Now, is there any point you think at possibly setting this equal to 0? Why not? It's not going to hurt anything, so let's try it. Let's first set it equal to 0. This may give us our zeros for the function. And what would that give us? Either got the product of two functions equal to 0, either x equals 0 or e to the x equals 0. So x equals 0, that's legitimate, right? Okay? And when you plug that in, you'll get 0. So 0, 0 is on the graph. So let me go on and start my function here. 0, 0 is on that graph. Okay? But let's look at the right-hand one. Is e to the x ever 0? Where? No, it's never 0. So that doesn't give us anything. So we got our one and only one 0 for the function, which happens also to be, that's our x-intercept, It's also our y-intercept, because when you set x equals 0, you get y is equal to 0. So 0, 0, that 1 point is all we get from the analysis of the function itself. Okay? Okay, so then what might we try next? Take a derivative, f prime of x. And what would that be? What kind of rule do we have here? Product rule. And what does that tell us to do? What does the product rule tell us? Okay, say that again. Okay, the derivative of the first, which is times the second, that'd be e to the x plus x e to the x, the first time derivative of the second, and that would be, so there's your first derivative, and what will we do with it? Set it equal to 0. And what could you do with that equation then? Factor, and what do you factor? Common factor, e to the x. What does that leave us with? Second, at 1 plus x, right? Equals 0. So again, we're back in the same dilemma as before. Either e to the x is equal to 0, or 1 plus x is equal to 0. Well, e to the x equals 0. When is that ever 0? Never. Okay? How about 1 plus x equals 0? When x equals negative 1. Okay, so that is a potential maximum or minimum. X equals negative 1. Okay? Let's plug in and see what we get when we put that. F of negative 1 is going to be what? Not really all that hard, is it? Negative e to the negative 1. In other words, negative 1 over e, right? And e was something of about 2.7 or so that's something close to negative 1/3. Okay? So when x is equal to negative 1, you're down here somewhere around negative 1/3. Okay, so there's your point there. And we think this is a, what did we not do at the very beginning? I forgot. And this is harder to do here, or is it? End behavior. What happens when x gets extraordinarily large? Where is that heading? Positive infinity. How about when x gets very, very negative? Okay, that's hard to say, isn't it? The x is going to negative infinity, but e to the minus x is going to 0. Who's winning there? I don't know. It's hard to say. So we can't really do an end behavior. That works much better on polynomials. On exponentials, a little tough. And that trig function, they gave us the end, so that's why we did the endpoints there. Okay. All right. So anyway, we've got that one. And we don't know where we're going over here. So what would you suggest we do next? Well, there's a couple things we probably should do. I think a second derivative is a great idea, so let's do that. We should have done something else, but we'll do a second derivative. And what will that be? Say again? E to the x plus And you're taking the derivative of the same thing we did before, that would be e to the x plus x e to the x, right? Because we were taking the derivative of that, that was exactly what we got there, and that's what we got, so we do that. So this is 2e to the x plus x e to the x. And then we're going to set that equal to 0, right? And where is that going to be 0? What do we do now? Factor e to the x, and what do we have left? 2 plus x. And when's that going to be 0? Is e to the x ever going to be 0? Nope. But this will produce x equal negative 2. So x equal negative 2, that's over here somewhere. Let's see what our function is there. So f of negative 2 is going to be minus 2e to the minus 2, which is going to be minus 2 over e squared, which is going to be something about like 2/9. So that's going to be right about there. Okay? Now I think we answered our question. Okay? The question is, who won? As x is going to negative infinity, the e to the x wins. So that's going to 0, x going to minus 1. This is getting closer and closer and closer and closer to 0. Okay? This one's going, you have a concave down here, has to be. It must be concave up here and concave up for the rest of it, because that's your only point of inflection. So this is your point of inflection right here. The little square there, I probably should make it green. That's what the book does. So it's concave down to here, 0 there, and going up here. So this is concave up from there on. There's your function. Okay? I'm so glad I didn't have to plot a lot of points there of that function. But using derivatives, boy, that makes it not too bad. Okay? Let's see what they got. Yes, it is, isn't it? Sad, isn't it? I can tell her voice is cracking. She's about to fall apart here. But there's your function, just like I tried to show. Let me blow it up a little bit. Okay. And there it is. 1 to 0 here. This is minus 1/9 here. And that's where it transitions from going concave down to concave up. There's your first derivative, so there's your local minimum, and it keeps going up from there. And e to the x wins again, not that way, but x is actually reinforcing it. It just goes faster. There's our function. Wow. And sadly enough, we're out of time. So, let me just make sure I got everybody here. I think I did. Just missing Shakina and Kia. Okay? So let's, for those who just came in, I need your, whatever test you haven't turned in yet, but let me return your others to you. Kia's not here. Ivory is. Angelo is. Let me set it down. First test, you have the second, and you have the first. Oh, okay. Oh, sorry. Okay. Angelo. That. Not giving me much to grade, are you? Okay. And then Shakira's not here. Jasmine. Here's your first test. You have your second, or your yeah, you do. Jason. And your okay, I can't run through this here. I'll give myself away and give it back like that. Okay. All right, test 2. Q is not here. Jasmine is. Jason is. And Jason. Sorry, I couldn't get these back to you sooner, but I didn't have them sooner. Oh, and the other thing, I knew y'all wanted something else. I could hear the grumbling in the background, okay? Especially from one. He was the one making all that noise. Okay. Why won't he give us the final? Okay. Here it is. Okay. Now, actually, when I looked at the first question, I thought, what are they talking about here? Okay. Let me give you, just to save you a little bit of effort here, on that first test, the first question. Estimate the roots of the equation using linear approximation of alpha of x equals square root of x. If I gave you that equation and said find the roots of it, what would you do? You might try something first. What would that be? Factor. In a short order, you'd find out it doesn't factor. So then what would you do next? If it won't factor, how do you find the roots of a quadratic? Say again? It's already set equal to 0. What do you do next? In fact, factoring you have it set equal to 0. But if factoring doesn't work, what do you try next? No, not yet. Think, what? Say again? Okay, how do you do that? That's what I'm asking. If factoring doesn't work, how do you do it? Think Math 100 or somewhere way back in the past. High school. Say again? Do you go to the second problem? Is that what you said? No, that's not what you do. What is it? If you can't factor, what do you go to next? What's always your fallback on a quadratic? On a quadratic formula, of course. Okay, when you do the quadratic formula on that, you're going to see what your roots are. Okay? And they're going to be irrational. So use the square root of x. Whatever, you're going to get a number there, right? Whatever it turns out being, you're going to get a number. Use that number to estimate your roots using the linear approximation for the square root of x. We did that earlier. We just didn't have it in quite this abstract of a form. So go back to the very first of the chapter when we did linear approximation. The first thing you do on that is do the quadratic formula. You'll come up with something that's the square root of something. You have minus b plus or minus the square root of something. Use that linear approximation to estimate the roots. The rest of them I think you can deal with pretty easily. Okay? That first one was a little bizarre. Now fairly bizarre. Okay. I think you can do the rest. I'll be in my office, by the way. Today I'm in class all day long. Okay, until 9 o'clock tonight. But tomorrow I'm in the office from 7:45 in the morning until 12 o'clock. And then from 12 o'clock, from about 2 o'clock until 5:15 I'm in the office. So if you need to come see me. If you get stumped, come see me between 7:45 and 12 and between 2 and 5:15. Then Wednesday I'll be in the office 7:45 in the morning until 9:15 at night. So come see me anytime then. I need these back by noon on Thursday because I've got a treatment on Friday. I won't be on campus at all. It won't do you any good to turn it in on Friday. If you turn it in on Friday, you're probably going to get it incomplete until I get back. Okay? So try to get it to me by noon on Thursday. I'll be here till 5:15, but in order to get grades in and everything, I need it really by noon. So try to get it to me by noon. I'll be here from 7:45 in the morning until 5:15 in the evening on Thursday. Don't bring it in at 5:14 and expect me to get anything other than incomplete. Well, I might be able to grade it, but please get it to me. Okay? Good deal. All right, I'll see you when you come bringing stuff back. I'll try to have your other tests and things ready by then. I'll try to have Blackboard updated by then.
I sent you my essay through the email.
You did send it?
I'm not sure if you received it or not. I got the email from just a little bit, so I'll hope.
Okay, I'll look at it, but you see, I'm not going to be in the office at all, except just little bits today. I'll try to find it tomorrow. Okay?
So,
Thank you.
What's your email?
cfowler@bostonstate.edu. It's on the facility. Oh, yeah, okay, you'll need to sign up for it, but what we'll have to do, you know somebody who did it, right? Right, so, I'll let you do that if you want to.
Okay.
Okay? But you'll have to register and everything here normally. Now, I think, where are you in school? At Auburn too? Okay, you'll have to do transient and all that kind of stuff,
Okay, I'll talk to you later.
Okay.
Wednesday. That's all.
Okay, good deal.